Welcome to my video on the counting circuit. Our first stop is the NAND gate oscillator. This chip operates using a principle called feedback, where its output is looped back as its input. The crucial elements here are two resistor capacitor networks, RC1 and RC2. Each network controls the time it takes for the input voltage to reach the required level to change the gate's output state. This feedback mechanism generates the essential clock signals. Now, these clock signals aren't your typical ticking clocks, but rather a series of voltage highs and lows forming a characteristic square waveform. Understanding these waveforms is the foundation for interpreting the functions of the subsequent components in our circuit. Moving on to our next stage, we have the decade counter. This component serves as a pulse counter, recording the number of clock pulses from the NAND gate oscillator. It's crucial here to ensure all input pins are properly conditioned. Conditioning involves making sure each pin represents a valid binary digit, either 0 or 1, to guarantee accurate counting. Our circuit's intelligence lies within the binary counting decimal up/down counter. This ingenious component accepts the decade counter's output and decides the count's direction, upwards or downwards. The direction is determined by the signal applied at the input pins. The chip's understanding of counting is fundamental to the overall operation of our circuit. Next in line is the 4511 IC. It takes the role of a decoder, translating the binary input into a decimal output. But it's not just a simple decoder, it's also a driver. This IC features several control pins, the blank, store, and lamp test pins. Correct conditioning of these pins is critical for the circuit's operation. For instance, the blank pin, when activated, turns off the display, whereas the lamp test pin illuminates all display segments for testing purposes. The final actor in our circuit play is the 7-segment display. This display brings to life the translated decimal digits, creating a visual representation of the counted pulses. Remember, there are two types of these displays, common anode, CA, and common cathode, CC. The type used in our circuit is the common cathode version. The difference: in the CC version, all the LED segments share a negative connection, whereas in the CA, or common anode version, all segments share a positive connection. Let's talk about resistors. Every segment on our display has its own dedicated resistor. Why is that? Well, resistors help control the current flowing through each LED segment. This regulation ensures that the LEDs have just the right amount of current to illuminate without overheating or burning out. The final step in our journey is housing all these components into a carefully designed case. The case not only physically protects the circuit, but also makes it compact and portable. One of the main challenges during the assembly process is to prevent the shorting of the PCB to the battery, which is resolved by carefully placing electrical tape on the battery. And there you have it, a comprehensive deep dive into a fully functioning counting circuit. We've explored its very heartbeat, the pulsating signals, the binary to decimal decoding, the count representation, all the way to its final embodiment in a sleek case. Thank you.